Welcome and good morning. Unfortunately, we're not actually going to be playing Fortnite, Max. Don't worry. It was just more of a slight April Fool's joke. I know people are a little sensitive to April Fools this year because life's already insane. But I had to do something, just a little something. How is everybody doing? How's it going? We hanging in there? What are we on? Week 2.5-ish? Yeah. Isaac's struggling. Isaac's got the struggles. Bad and sad. Oh, no. Hi, Bryce. 8.25 out of 10. That's not too bad, Max. That's not too bad. Bored is a for sure one, man. Um, we've started just like going on walks around our neighborhood um, because it's like all you can do. And playing in our backyard. Our backyard's not too bad. It was really nice yesterday. I know all the April Fool's jokes are just so lacking today. Um, yeah. So Max, someone was saying that my mic is a little jacked up. I don't know. I'll have to troubleshoot that and see if there's something wrong with it. I'm glad you've enjoyed it, Austin. Yeah, I didn't do anything to the mic. I don't know why. Yeah, Honors was saying it was sounding weird too. I might have to mess with it and troubleshoot it a little bit. I wonder if something got jacked up. Wow. We'll see. We'll see. Yeah, I hope it didn't get knocked. Um, huh. Well, we'll see. Hi, Drake. Get out of here. Okay. We'll see. I'll mess around with the microphone settings and see if I can fix it. If it's something that can be fixed. Um, we'll see. We'll see. We'll see. We'll see. I haven't done anything with it. I don't think my kids messed with it. So, how much worse can I make it? Oh, I could probably make it pretty bad. I'll try unplugging it, plugging it back in, but I don't want to do that right now since we're already live, um, with the stream and everything. So as long as it's not terrible, we'll move forward with it. Got your valence electrons, Isaac? Good, I'm glad. I have infinite valence electrons, so oh man, tired. Okay, I do want to go ahead and talk about a few things that are on the canvas. I've updated a couple things. If you haven't realized it yet, the canvas is going to be like the main hub for what we're going to be doing over the next month. So always make sure that you're checking and updating and looking at Canvas. No, just a fancy shirt, Sammy. I'm lazy. It's that classic meme about video conference interviews. Got business up front, and then I'm just wearing gym shorts. Okay, so let's look at the yeah, let's look at the canvas. So on the canvas, Um, I'm glad. All right, so on the canvas, right? So this is the homepage for the canvas. If you haven't checked the calendar, make sure the calendar. This is, of course, my daily schedule, what I'll be doing every day. Today's Wednesday, so we're on the AP Chemistry stream. Modules are going to be where you want to go to keep up with the class. So if we go over to modules, right? If we go over to modules, you'll see all this stuff. So we've technically already done this quarantine to-do list. So you can just minimize that and get that out of the way because I'm not going to be adding anything else to this quarantine to-do list. What we're going to be mostly adding to is we're going to be adding to, we've got the 2015 exam, and then we have the AP test review streams. And so these are the ones that you're going to see most of this stuff pop up. Yeah, it's a little bit lagging behind, but it shouldn't be too bad. Just a couple seconds. All right, so you have your 2015 free response questions. These are the ones that you could actually download it. So if you download the 2015 response, go ahead and download and work through it. You can skip most of problem 1. We talked about that. Okay. And then I just uploaded this morning the grading and the submission. So make sure you can download the grading key here. Look at the grading key. That tells you all the scoring guidelines, tells you how many points you get for each problem, tells you what you need to have to get those points, those kind of things. So make sure you look at that, score yourself, and then go ahead and upload your answers. Nai, if it's that bad, you might want to try reloading the page. It should only be 2 or 3 seconds. Yeah, so yeah, try reloading. Oh gosh, Isaac. Okay, so everybody understand what's due on Canvas and how to do Canvas and what I'm expecting of them to have on Canvas. Because it's due tomorrow night. Apparently. Isaac's very sassy today. If you do a factor label, it includes a calculation they ask for, but you don't write out the exact answer to get points for it. It depends on the problem. You'll have to see, there are no half points. So if a problem is worth 2 points, you might get 1 out of the 2 points, depending on how the grading key is written. But if a problem is just 1 point, you'll get nothing. So it's a little intense on how it's graded. Okay. Any other questions on any of this stuff? We're going to dive into reviewing Unit 2 here in a second. So, there's usually only on the full exam, it's usually only one. No, it's just water. It's just water. It's usually only 1 or 2 points that are graded strictly on units. I would advise you guys as you go through the grading key that you kind of study, look at the wording a little bit, look at how the AP graders are going to be looking at problems to kind of see, narrow in on what you're going to need to get the points. Reminder, on Friday, we're going to be going through all the answers and I'm going to be showing you everything and we're going to answer questions that you guys have on that 2015 exam. So make sure you get it done and scored and put in to before tomorrow night at midnight so that on Friday we can spend the class going through it. If you get the first part wrong, we use that number right, the method for other parts. Yeah. So you would grade it. So that the way we've been grading the spillover problems, if you have to use an answer from part A to say do part B, if you get part A wrong but you use it correctly in part B, then you get those points. They've moved away from those problems in past years, but they still have a couple that spill into the next problem. So yeah, those you should give yourself points for. Okay, good. Other questions? Okay, if there aren't any others, let's dive into the Unit 2 review. So it's going to be, if you skip problem 1, it's going to be probably around an hour to an hour and a half. So probably like an hour, Isaac. Probably, Maggie. I'd have to look. I'd have to look at specifics like that. How long should we take if we do all the problems? So I already said that, Isaac. So the whole thing. So technically, the AP test gives you 105 minutes on the classic free response. So that's what, an hour, hour 45. So yeah, so the whole thing at maximum should take an hour 45. You guys can probably do it in an hour and a half, hour 15, because I've conditioned you guys to go fast. So basically, yeah, you guys are special. All right, let's dive into the Unit 2 review. If we have more questions and more things about specifics, so Maggie, like on that one, yeah, I know, we already talked about it, Micah. There's something up with my mic. I might just have to replug it and do something, kind of troubleshoot it. So yeah, I don't know what's going on with that. So yeah, we'll have to see if I can fix that. Okay. Let's go into Unit 2 review. Micah, if you were here on time, that suggestion has already been made. All right, so Roman number 2. Let's... Boop. Roman number 2, Unit 2. Okay. So Unit 2 has to do with basically, we can call it compounds. So the first thing we're going to talk about is that atoms bond to form compounds. Okay, number 1. So we have different types. So let's do types of compounds. Really, it's like the forces that underlie our different types of compounds. So first thing we want to talk about, kind of to build into this, are electronegativity values. So remind me again, what is or what was electronegativity? Excuse me. Yeah, so how much it pulls on the electrons. Thanks, Micah. So electronegativity is how much it pulls on the electrons. And we say that fluorine is the greatest. So fluorine has our greatest electronegativity value. And so if we look at, a periodic table, okay, as we go to the top right, fluorine is the most electronegative. The noble gases have kind of a drop-off. And then francium in the bottom left. has one of the lowest electronegativity values. Okay. So yeah. Okay. So letter B. Valence electrons shared between two atoms so valence electrons shared between two atoms with similar electronegativities forms a covalent bond. Okay. So the valence electrons shared between two atoms with similar electronegativities forms a covalent bond. Particularly, I guess I should throw this in here, a non-polar covalent bond. So example would be like carbon to hydrogen. Even though carbon and hydrogen have slightly different electronegativity values, they're close enough to each other that we would consider a carbon-hydrogen bond to be mostly nonpolar. I mean, a better example would maybe be like, you know, a Cl-Cl bond. Or a carbon-carbon. Yeah, of course. Okay, so letter C, we would say polar bonds if polar bonds form if there's a difference. So for example, something like HCl. I'm glad, Mikey. I'm glad you got some nice breakfast sandwich. I haven't eaten breakfast yet. I'm gonna go eat after the stream. So because chlorine is more electronegative, the chlorine is going to pull on the electrons, which is going to result in a partially negative chlorine and a partially positive hydrogen, right? So the chlorine end of the molecule is going to be negative, the hydrogen end of the molecule is going to be positive, and we say that this is a polar covalent bond. Ham, egg, and cheese, classic. Okay. Marcus can take AP if he wants to. That's totally fine. Gotta have bacon. Okay, so polar covalent bonds. Good. That's all I want to say about that. Let's go to a little letter D. So, little letter D, we also want to talk about how this is kind of like just in general. Generally, two nonmetals makes a covalent bond. Makes an ionic bond. Okay, letter E. Metallic solids. The valence electrons are delocalized. they're not attached to individual atoms. Okay, so lots of stuff here, right? Lots of things to go to. This is kind of just like a random smattering of stuff is the way the AP test has this organized. But basically, when we talk about bonds, we have different types of compounds, right? And the thing we want to look at for types of compounds is we want to look at electronegativity differences. So electronegativity differences, if there is no electronegativity difference between two bonded atoms, we would say that it forms a nonpolar covalent bond. Specifically, we're going to be talking about nonmetal atoms here. When we say that the bond is polar, that's if there's a difference in the electronegativity. And so if one atom pulls on the electrons more. Now, if there's a large difference in electronegativity, that usually results in an ionic bond, because at that point the nonmetal atom can remove the electron from the metal. Okay, and then, and this is kind of where we get to the general idea that two nonmetals makes a covalent metal, and a nonmetal makes an ionic. But it really is a spectrum. There's not like a defining cutoff between what we would consider to be ionic and what we consider to be polar covalent. There is some give or take. And then lastly, metals being their own thing. So if you have bonds between two different metals, we would say that those valence electrons are delocalized. So we don't worry about electronegativity differences. Sarah, that's a hard question. So the actual, the bond itself, covalent bonds are a little bit stronger, but we usually don't break those covalent bonds unless we're doing, very high energy stuff. But if you think about a diamond, right? A diamond's a really good example of a structure that has all covalent bonds. And so covalent bonds in that case are going to be a little bit stronger. But there's all kind of other factors that come into play. There are going to be ionic bonds that are stronger than covalent bonds, and there's going to be covalent bonds that are stronger than ionic bond. It's kind of difficult to put a tend on it. So. Okay. Number 2. Let's look at potential energy diagrams. Okay, so if we make a graph with potential energy on our y-axis and radius on the x-axis, we could describe, what are the forces that come into play when we form a bond, okay? And so the graph kind of looks like this, right? With out here being two totally separate atoms, okay? Down here we have two bonded atoms, and then up here you have the two atoms kind of on top of each other. Okay, are there cases in which a metal and a nonmetal form a covalent bond? Yeah, there are. Let me pull up periodic table. Lithium and beryllium. Beryllium especially is notorious for forming covalent bonds. Uranium can do it as well. UF6. It happens more than we like to simplify in general chemistry, but yeah, so. Okay, all right, so totally separate, perfect distance, totally far apart, okay. No, you don't need to know exceptions, Bryce. Just know that if a problem tells you that a compound is, covalent or something, you don't ever be like, oh no, they're wrong, right? If they tell you an exception, you just kind of have to be like, oh, that's interesting. I could see how that would work. So yeah. So let's go back to Isaac's question. So I mean, like, so imagine you have two atoms, okay? So there's an attraction between these two atoms, okay? There's an attraction to the other electrons from the other. So this atom is attracted to this one's valence electrons, etc. Yeah, I will. I'm getting there. I'm getting there, Lauren. All right. So when the atoms are totally separate, we can imagine that the force between them is essentially zero. This dotted line is my attempt to represent zero, right? So this is where there is no attraction between the two atoms. Okay. Now, as the two atoms come together, right, that attractive force between them starts to pull them together, right? And there is an ideal distance where there's an ideal radius that maximizes the attraction between the two atoms. But what happens is if you try to start pushing them on top of each other, the nuclei begin to repel one another. And so that's why the energy goes back up, is because the nucleus of the one atom, which is positive, and the nucleus of the other atom, which is positive, repel each other. And so there's this balance between the attraction to the electrons and then the repulsion from the nuclei, which is why we get this sweet spot right in the middle that has us our ideal bond distance. Okay. Does that make sense? Does this diagram make sense? Basically, it's saying there's a specific radius that gives you the strongest bond. It's almost like the Goldilocks analogy, right? It's not too close, not too far, but just right. Perfect. So no. This isn't like a time thing. This is just considering an atom, right? So the idea is that if you take two free atoms and you start to bring them closer and closer together, right, we would be traveling along this curve down to here. Okay. So yeah, if you take two atoms and bring them together. So yes, the lowest potential energy is the most stable position, Sarah. Yes. So Haley, yeah, kind of. We would think going from right to left as you bring the two atoms together. It's technically called, uh, what's it called? Um, yeah, I guess you could technically call this internuclear distance. That might be a better labeling for it. Okay, cool. Next idea. Okay. So another little letter B here, right? What determines the strength or the length and the ideal length of a covalent bond? So covalent bond length, right? So what makes a shorter covalent bond? How could we get a shorter covalent bond? How could we get the two atoms to come closer together? Yeah, more shared electrons. So that's called bond order. So you get, let's see, so you have a shorter length with higher order. And when we say by order, we mean single, double, triple bond. And then smaller radius. Yeah, so shorter length. It's interesting, Isaac. It's not, or Logan. It's not actually the electronegativity. The electronegativity is not going to affect the size or the length of the bond. Well, I mean, not directly. Indirectly, it's this idea of radius, because we know that smaller radii atoms, atoms with smaller radiuses, radii, it's such a stupid word, um, are going to be closer together because they have higher electronegativity values and because they're smaller. So it's kind of like all those factors come into play. So we're going to say that we can get shorter length with a higher order, so a single, double, triple, etc. So a triple bond is going to be shorter than a single bond, and with smaller radius atoms. And then I guess I should kind of tack on one last thing here. Shorter equals stronger. Which is the same thing as saying it has a higher bond energy. Okay, cool. What about ionic bonds, right? What determines ionic bonds? So let's not do length here. Let's do strength. So what makes for a stronger ionic bond? Smaller radii again. Yeah. I'm going to put smaller radii as the second one. Oh gosh, the chat just got flooded. Yeah, charges. Good. You guys got charges. So greater charges. All right. So if we have ions together and they have greater charges, the greater charged ions are going to be stronger, as well as if we have smaller radii are going to be stronger as well. So if you're trying to look at it, and Sarah, it actually doesn't. The difference in electronegativity is secondary. It doesn't actually matter. Stronger ionic bonds come from greater charges of the ions and smaller radius. Well, yeah, those are kind of where we got the exceptions to the solubility rules. Those are the insoluble compounds. Okay, cool. Yeah, the AP test doesn't actually talk about metallic strength, so I'm just going to skip that. So let's go to big number 3. Ionic structure. So how is an ionic crystal structured? What does an ionic crystal look like? Yeah, we have crystal lattice. Yeah, good. Crystal lattice. As Isaac described it, we have positive, negative, positive, negative, negative, positive, negative, positive, positive, negative, positive, negative in a three-dimensional arrangement. Okay, and that's pretty much it. Ooh, look at that! Look at that in the chat. Look at that excellent diagram. Um, yeah, Zach, you should, yeah, technically add space. Anyway, okay. So that's all you need to know about ionic crystal structures. Remember in class we learned like body-centered cubic, face-centered cubic, those things. Those are not on the AP test. So you guys are good. So don't worry about that. So number 4. What about metal structure? So how do metals exist in a metal? Yeah, we have the sea of electrons. Right, where we have our positive, 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 and then the electrons are delocalized. Right, randomly spread throughout. Maybe we'll circle these. Okay. Yes, much better, Zach. Thank you. All right. Okay, and then we also kind of want to make a little side note about alloys. There were 2 types of alloys. What were my 2 types of alloys? Do you guys remember the 2 types of alloys? It's been a long time since we've talked about alloys. Substitutional is one. Right, and so this would be something like brass, where you had like copper, 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 and then to form an alloy, you replace, one of them with zinc. So it's where one substitutes for another. So our copper, our zinc atom replaces, this copper. That's a substitutional alloy. What's our other type of alloy? I don't know if you guys remember. So the other type of alloy is called interstitial. This is something like steel. We have iron, 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 iron. And then you randomly put a carbon right in the middle. Okay, so substitutional alloy is where one element replaces another. Interstitial alloy is where you kind of shove a carbon in the middle of the crystal structure. So you take a smaller element. We learned this way back in honors chem. We didn't actually really talk about it all that much this year, but that's because it's really simple. So substitutional interstitial, basically one element replaces another for a substitutional alloy, and then a smaller atom replaces or fits in between some bigger atoms for substitute or interstitial. And that's all you have to know. Yeah. So technically we learned it in honors and didn't really talk about it in AP. But okay, cool. Interstitial, the more small atoms in structure, the more brittle. Yeah, it starts to take on more of an ionic characteristic as you add more and more of these smaller atoms in there because it makes it more and more rigid. And so it's hard to find the trick is finding the balance between strength and brittleness, which is what, the whole steel industry is built on. Okay, so let's see. That's A. Now we're on to B, big B. Everyone's favorite, Lewis structures. So simple Lewis structures, I just picked two random ones off the top of my head. Something like water and something like methane. So we have bonded electrons, we have lone pairs of electrons, right? It's all based on the number of valence electrons, and we bond atoms and put things together and do things like that. Okay, so just make sure that you can, draw simple Lewis structures. So we also need to talk about resonance and formal charge. So first off, resonance. Remind me, what is resonance? Yeah, multiple possible Lewis structures, right? It's when we have equivalent Lewis structures. So a simple one is like the nitrite ion, so NO2 minus. So the nitrite ion has the structure N right? So yeah, it has a 1.5 bond because the true structure is the average of the two. It's the fact that we can draw one structure with a double bond on the right oxygen and then one structure with a double bond on the left oxygen. And that gives us our resonance, which is the true structure is the average of the two. And so we would say instead of having a single and a double, we have like a 1.5 bond between both oxygens and between the nitrogen and the oxygens. Now, formal charge, if you remember, formal charge looks at it looks at how many electrons are around an atom versus how many it should have. So let's pull one of these nitrate ion structures just for reference. So if we look, so if we pull up a periodic table, Lauren, remember that our valence electrons go 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So our noble gases have 8, fluorine would have 7, oxygen has 6, nitrogen has 5, right? So nitrogen should have 5 and oxygen should have 6. So if we look in the structure, right, remember the bond is made up of 2 electrons, and so we can kind of like chop the bonds in half. Right? So if we look at this left oxygen, around this left oxygen we have 1, 2, 3, 4, 5, 6, 7. It's sharing to have 8, but it currently has 7 around it. And so this oxygen has an extra electron. And so we would say that this oxygen has a -1 formal charge. The center nitrogen, 1, 2, 3, 4, 5. Nitrogen starts with 5, it has 5. And so this center nitrogen would have a formal charge of 0. This right oxygen, 1, 2, 3, 4, 5, 6, started with 6, it has 6, so it also is going to have a formal charge of 0. And so in this structure, we only have one formal charge, and that's on the oxygen, and it's a -1. So it does match up. So the formal charges, if you sum the formal charges, they will add up to whatever the charge of the species is. And so because nitrate has a -1 charge, the formal charges will add up to -1 because we added an extra electron when we drew the structure. So the best structure has formal charges closest to 0. Okay. So formal charge and resonance, both ways to determine how good a Lewis structure actually is. Okay. Cool. All right. Let's move on to number 3. Vesper. Vesper. Right, so what was Vesper? Isaac. What's Vesper? Apparently it's Isaac's worst nightmare. Valence shell electron pair repulsion, right? Valence shell electron pair repulsion. It has to do with geometries, right? So it allows us to predict geometries. So we can talk about geometry. All right, this is where we get, our linear, trigonal, tetrahedral, etc. Valence shell electron pair repulsion. Yeah, Maggie. Okay. So we also have things like bond angles. Okay, 180, 120, 109.5. So you should have a giant chart somewhere. Yeah, so you have to have that chart memorized. So you should have a giant chart that you have memorized and can look at and make sure you know. I'm not going to recreate the chart here because that would just take too long. Let me see if I have a website. This page out of a random textbook has a bunch of them. From Libre Texts. Yeah, Isaac probably still has a chart, so Isaac could maybe drop that in the Discord at some point. So you guys can use that as a reference. I should have one somewhere too. I'll look and see. Yeah, we'll let Isaac post the one he's got. All right, so then we can also predict polarity based on things like symmetry, which that's not how you spell symmetry. Symmetry has 2 M's. Symmetry and electronegativity. Okay. We also need to know hybridization. Actually, maybe we'll do that as a fourth thing. Hybridization. Right, so remember we had SP, SP2, SP3, SP3D, SP3D2, right? So we have our different hybridizations, and these just associated with the geometry, right? If something was linear, it was going to be SP. If it was trigonal, it was going to be SP2. If it's tetrahedral, SP3. Trigonal bipyramid, SP3D. Trigonal or octahedral, SP3D2. Okay. Yeah. You don't have to know like what the specific hybrid orbitals look like or things like that. You just have to know how it corresponds with the geometries. And then we have to know this last thing. Sigma and pi bonds. So if we look at a structure like this, right, if we were to just count sigma and pi bonds, we would see that, in this structure, we have 1, 2, 3, 4, 5, 6, 7 sigmas, and 1 pi. Okay, so remember when we talked about sigma and pi bonds, every bond is a sigma bond, and then if we have a double or a triple, that double bond is our pi bond. Okay, and then in general, I want to just put this right last here. Pi bonds are weaker than sigma bonds. So when we talk about the double bond between this C and this O, it has to do with how the electrons are overlapping in a sigma and pi bond. If you remember, so if I were to just draw this out, CO, the sigma bond is formed from a direct overlap, something like this, right? That's my sigma, and then the pi comes from this above and below idea, right? So our pi bond is not like in the axis of the bond itself. The electrons are kind of more towards the outside, and so they're easier to break. And so when you talk about a double bond is going to be stronger than a single bond, but the pi component of the double bond is weaker when you just compare it to a single bond, right? But summatively, this bond is stronger than a single bond, but these pi bonds are a little bit weaker. Okay, hopefully that answered Isaac's question. All right, we are out of time, and this was the last thing for Unit 2. So the biggest thing that I think you guys are going to need to go back and study and learn and recognize is going to be your Vesper geometries, your Lewis structures, get a little more practice drawing Lewis structures because everyone's a little rusty on that. Thanks for the follow, Jedi Master Soda. Appreciate it. Yeah, right on time, right on schedule. Okay. So yeah, any last questions about Unit 2? Don't forget you need to do the chapter or the 2015 free response. Get that submitted up on Canvas. Grade yourself. Get all that stuff done before tomorrow at midnight so we can talk about it on Friday. If you have questions as you're doing anything, as you're grading yourself, as you're going through problems or things, I'll be in the Discord this afternoon from 12 to 2. If there's no other questions, Isaac, thanks for the follow, Isaac. Appreciate it. Don't know why you hadn't followed me yet. Baby, don't hurt me. Don't hurt me no more. What's a thing where an atom can have more than 8? So that's expanded octet, right? So that goes back in the geometry, how we can have, that's where we got the trigonal bipyramid and the octahedral. That's when we had expanded octets. Cool. Okay, I think that's it. We're going to end with that. Let me go on. Yeah, if you have other questions, make sure to ask in the Discord or send me an email or message me on Canvas or all these things. Make sure you're keeping up to date on the Canvas. Yeah, they do have a couple expanded octets on the AP test, Max. So make sure you're aware of those geometries and how to use those and how to do those. So, okay, I'll try to figure out what's going on with my mic. So hopefully by Friday we can have some better quality. Okay. Have a good night, guys. Or I guess not good night. Have a good rest of the day. Bye.